Hello guys and welcome you all in the problem solving class of the course Applied Electromagnetics for Engineers. I am Vivek Kumar Srivastav, PMRF Research Scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper. So in the today's class we will see some numerical based on the topics Biot-Savart law and Ampere's law, which is covered in the week 8 of this course, and then at last we will see the inductance calculation based on these basic laws. So let us start. So, so our first problem is uh, a 4 centimeter long solenoid carries a current of 400 milliampere. If the solenoid is to produce a magnetic field density or say magnetic flux density of 6 milliweber per meter, then the required number of turn of the wire is. So basically here we have to find out the number of turns that is present in the solenoid. Okay, by assuming that these terms are given here, that is length of the solenoid, then current flowing through the solenoid, and the magnetic flux density is given to us, and then we have to find that how much number of turn required in the solenoid such that it can produce this much amount of field. So before proceeding and finding out the number of turns required, we have to first derive the expression of magnetic flux density that is existing inside the uh, solenoid. So let us consider that this is the solenoid, okay, and the total length of this solenoid is capital L, and the current flowing through this solenoid is I, and yeah, the turn density N is defined as total number of turns present, total number of turns present per unit length of the solenoid, that is in meter. Okay, so if suppose the length is given to you, then for finding out that how much number of turns present in the solenoid, what we have to do, we have to just multiply the turn density with the number of sorry, total length of the solenoid. Okay, so that's how you can determine that the how much number of turns present in this solenoid. So for finding out the magnetic flux density that is present inside this solenoid, what we will do, we will use the ampere circuital law. Okay, so let us first take the amperian path. So let us say that this is the amperian path that I am considering. So I am defining the points here as PQRS. Okay, and the uh, direction along this path taken as given here in this figure. Okay, so as we all know that Ampere's law states that the line integral of H dot dl is defined as total current that is uh, flowing inside this Amperian loop. Okay, so we will use this Amperian circuital law. So for determining that what will be the magnetic flux density that is present inside this solenoid. Okay, so uh, as in the question it is given that we have to find magnetic flux density. So what I will do, I will replace this magnetic flux intensity in terms of magnetic flux density, so that we can directly use this formula for determining the number of turns. Okay, so as we all know that magnetic flux density B is defined as mu naught times H. Okay, so we will replace the value of H uh, by uh, B by mu naught. Okay, in this expression here. Okay, so the line integral is defined as B dot dl is equals to mu naught into I. So now what I will do, I will break, for determining the magnetic flux density, I will break this line integral into four along this fourth path that is defined as PQ, then QR, then RS, and then SP. Okay, so I will break this integral into four path. that is PQ, then QR, then RS, and at last SP, and this will be equals to mu naught times I. Okay, so this dot this product term is inside this integral term is written as, let me assume that here the field is bi, that is inside this solenoid. Okay, bi into dl, this will be equals to cos 0. Okay, because field is along this direction. Okay, and length is also in the same direction, differential length, so that's why I am considering it here as a cos 0. Similarly, here we define as b dl cos 90. Okay, because here field is along this direction. Okay, along the right side, whereas the differential length is orthogonal to this direction of b. That's why here I am considering it as a cos 90. Now along the rs, the angle will be equals to cos 180 degree. Okay, whereas for sp, the angle will be equals to cos 270 degree. Okay, so as we know that the mm, value of cos 90 is equals to 0, similarly value of cos 270 is equals to 0, so the remaining term is the line integral along pq and the line integral along the rs. Now, yeah, so let me change the color. So yeah, so here we uh, define this dl as, yeah, or what we can do, we will directly take the integral, so this becomes equals to b dot l, because the length of this uh, amperian path is l. Okay, bl plus, here the value is equals to bo into l with minus sign, because it's cos 180 degree is equals to mu naught into I. Now we have to see here that if suppose the amperian path width of this amperian path is greater than the radius of this solenoid, so if suppose the current flowing in this solenoid in the upper side is out of this plane, whereas for this lower uh, part of the solenoid the current is inside this plane, so the net field that is along this path will cancel out each other, so that's why b naught will be equals to 0, so this term is also 0 here. Okay, so this bi is defined as mu naught I dot l. Okay, now one thing that we have to see here, that this current we have taken inside this, the total current that we have taken inside this amperian loop is I. Okay, so I is defined as n times small I, means this is the total current, sorry, this will be small I, and the total current that is flowing inside this amperian path will be capital I. So the relationship between capital I and small I is n times I, where n is the turn density. Okay, so we have to replace here capital I as mu naught n into I, where I is the current flowing through this solenoid. Okay, now, so this b is defined as mu naught n I by l. Okay, so the we will determine the value of n from by using this expression, so n will be equals to BL by mu naught into I. Okay, so the value of B is given here. Total length of the solenoid is given in the question, that is 4 centimeter. Current is also given, that is 400 milliampere, and the value of mu naught, as we all know, that is 4 pi into 10 raised to the power minus 7. So by putting these values we can easily determine the total number of turns that is required in a solenoid for producing this much amount of field. Okay, so the calculated number of turn will be equal to 478. Okay, so that's how we can calculate the number of turns required. Now moving ahead, the next problem is, if the magnetic vector potential A is defined as minus rho square by 4 Az Weber per meter, then the total magnetic flux crossing through the surface uh, means in yeah, phi is fixed here, and rho and z we are varying. So the question is that how much magnetic flux we have to determine the magnetic flux that is crossing through the surface. Okay, and the differential surface for this is defined as d rho dz, because only rho and z is varying, phi is constant here. Okay, so this will be differential surface through which we have to find that how much magnetic flux is crossing. Okay, so here for finding out that how much flux that is crossing through the surface, we will use this formula, that is phi is equals to integral b dot ds, surface integral b dot ds. Now as in the question it is given the magnetic vector potential, so for finding out the magnetic flux density we will use this relation b is equals to del cross a. Okay, so by using this expression we can easily find out the value of magnetic flux density. So let us determine this expression. So this will be equals to a rho, a phi, and a z, and yeah, this will be equals to del by del rho del z. Okay, and then this will be equals to 0 0 and minus rho square by 4. Okay, so here we can see that the value of b that is comes after calculation is defined as minus del az by del rho into a phi. Okay, so you have to differentiate the value of az, means here the vector potential is having only the jet field component. Okay, so you have to put the value of a here as minus rho square by 4, and you have to differentiate this with respect to rho. So after differentiating with respect to rho you will get rho by 2 a5. Okay, and differential length we have already seen that this will be equals to d rho dz into a phi. So now we can easily calculate the value of phi, which will be equals to b dot ds. So we have to put the value of b as rho by 2. Okay, and we will uh, put the value of ds as d rho into dz, and the limit that we have to take is rho is from 1 to 2 meter and z is from 0 to 6. Okay, so I think here it is written wrong, it's a 6. Okay, so once you calculate you will get the flux that is crossing through the surface will be equals to 4.5 Weber. Okay, so let us move ahead to the next question. So here is the next question. In a certain conducting region, the H is given as YAX minus XAY ampere per meter on plane Z is equals to 0. Using the information to solve question 3. Okay, so basically h is given here this much on the plane z is equals to 0. So now we have to determine uh, the value of current density that is in the present question, and based on this we have to determine the next problem as well, which we will see later. So right now we have to determine the current density. So for that we know that the relation J is equals to del cross H. Okay, so we will use this expression for finding out the current density. So this we can determine as del by del x, del by del y, and del by del z. Okay, and this will be equals to, sorry, this is equals to ax, ay, and this is az, and this will be equals to y minus x, and this is 0. So from here we can say that ax is equal into 0 minus ay into 0 plus, yeah, this will be equals to minus 1 into az. Okay, so this will be equals to minus 2 az. So this is the current density that we can calculate by using this expression. Okay, yeah, so this much ampere per meter square is the current density that we have calculated. Now in the second question, which is related to the previous one, we have to determine the current around the edge of the rectangle. Okay, so if suppose this is the rectangle, yeah, so along z is equals to 0, x varies from 0 to 2 and y varies from minus 1 to 5. Okay, we have to determine the current that is uh, flowing through this rectangle. Okay, so I we know that it is defined as surface integral of j dot ds. Okay, so the value of j is, we have already calculated, is equals to minus 2 az. Okay, so this will be equals to minus 2 into, we have to take the differential surface area along the AZ. So this will be equals to dx dy, and we have to take the limit as 0 to 2 along x and minus 1 to 5 along y. So by using this expression we can calculate the current. Okay, so after calculation you will get minus 24 milliampere is the amount of current that is uh, flowing through this rectangle. Okay, so the next question is, a current carrying wire is bent into a semicircle. If suppose this is a semicircle, okay, this is the semicircle. Okay, so this is a current carrying wire. The current flowing through the wire is 10 ampere, so current is also mentioned here as a 10 ampere, and that the radius of the semicircle, which is r here, let us say it is equals to 4 meter. So we have to calculate the value of magnetic field at the center of this semicircle. Okay, so for finding such kind of for finding magnetic field for such kind of structure, what we will do, we will take the expression of Biot-Savart law, which is defined as mu naught over 4 pi integral I dl cross ar over r square. Okay, so yeah, so current I is already given here, that is 10 ampere. Okay, dl we have to first find out. So let us suppose this is the differential length, which is ds. Okay, so ds is defined as, ds here is the differential length, don't confuse it with the differential surface. Okay, this is the this is just a variable that I can choose anything. Okay, so I am considering here as ds. Okay, you can take it as dl as well, but I am considering here as ds. So this is defined as r d phi into a phi. Okay, and ar we can calculate as vector r over mod of r. Okay, so we have to first calculate the vector r here. So vector r, or we can directly calculate it as, we can directly calculate it as ds cross r cap. Okay, so this will be equals to ds into r, means it's a unit vector, so magnitude will remains 1 into cos, sorry, sine 90. So this will be equals to ds, means the value of ar is r d phi. So we have to just put the value of ar here and dl here. Okay, or say ds. So we can determine the value of b as b naught over 4 pi into I, we can take outside here. Okay, and this will be equals to, yeah, so this will be equals to r d phi. Okay, over r square. So this will be cancel out. So that's how we can calculate the magnetic field. M naught I over 4 pi into this will be equals to, yeah, so this will be equals to pi, because we are considering here as semicircle. So this will be the phi will vary from 0 to pi. So after calculation you will get pi, and this will be equals to r. So this pi will cancel out, and the magnetic flux density expression that we will derive here as mu naught I by 4 pi, sorry, 4r. Okay, so we will use this expression. Okay, and the value of current is already given to us, that is 10 ampere. The radius is also given, so the value of r is also given, that is 4 meter. The value of mu naught, we know that 4 pi into 10 raised to the power minus 7. So we will put these values here in the expression, and once we calculate the calculated magnetic flux density, that is equals to 785.4 nanotesla. Okay, so that's how we can calculate the magnetic flux density. So now moving ahead, so here in this question we have to find out the magnetic field at point p. So here is the point p from a wire segment. Okay, so this is the wire segment. Okay, this is the wire segment. So from this wire segment we have to find out that how much magnetic flux density that is present at point p. Okay, so this is the problem. So here in the question it is given that the current that is flowing through this uh, wire segment is I. Okay, so from this current segment how much magnetic field that is generated or say produced at this point, that we have to calculate. So what we will do here, we we have to take the uh, Biot-Savart law for determining the magnetic flux density, which is defined as B is equal to mu naught over 4 pi integral I dl cross vector r over, or say it's a capital R cube. Okay, so for determining the vector r, what we have to do, we have to first take the we have to first determine the coordinates of this uh, line segment and the point P. So here in the uh, figure it is shown that point P is defined as rho comma 0 comma 0. Okay, so in cylindrical coordinate this is defined as rho comma 0 comma 0, whereas the coordinate of this small line segment, which is dl, is 0 comma 0 comma z. Okay, so vector r is defined as rho comma 0 comma 0 minus 0 comma 0 comma z. Okay, so this will be equals to rho a rho minus z a z. Okay, so rho is defined like that. Sorry, vector r is defined like that. So capital R, which is the magnitude of this vector r, is defined as square root of rho square plus z square. Okay, so and also the value of dl, that is particularly for this problem, is defined as dl is equals to dz into az. Okay, so this quantity we already know, so we have to just put this in this expression of magnetic flux density. Okay, so what we will do, we have to first evaluate the dl cross vector r, so that it will be easy for us. So this will be dz into az cross, yeah, this will be rho a rho minus z az. Okay, so that we can determine, so this is a rho a phi and a z. Okay, and this will be equals to 0 0 dz, and this will be 0 sorry, rho 0 minus z. Okay, so this will be equals to a rho will be 0, a phi will be the component of a phi will be rho dz, and similarly az component will also 0. So the value of dl cross vector r is obtained as rho dz a phi. Okay, so we have to put this here. So this magnetic flux density B is defined as mu naught over 4 pi integral rho dz over rho square plus z square raised to the power 3 by 2. Okay, so and the direction is along a phi. Okay, a phi means into this plane. Okay, into this page. Okay, or say into the screen of your mobile, or say laptop, whatever it is. So we have to determine this integral for finding out that how much magnetic field that is generated at this point P. Okay, so for determining this integral, what we have to do, we have to use substitution method. So we will put the value of z as rho cot alpha. Okay, so this alpha is defined as angle that is subtended in between the differential length dl and the vector r. Okay, so this we can substitute. Okay, so dz we can find out as minus rho cosec square alpha. Okay, so this we can put up here in this expression. So B is obtained as mu naught over 4 pi integral minus rho square cosec square alpha dot d alpha. Yeah, here d alpha I am missing. So, and on the bottom side this will be equals to rho cube cosec cube alpha. Okay, so this cosec square will cancel, and this rho square will be cancelled, and the limit of this integral is from alpha 1 to alpha 2. Okay, so this we can calculate. This will be equals to mu naught over 4 pi rho, and this will be integral from alpha 1 to alpha 2 minus, we can take here outside this integral, and this will be equals to sine of alpha dot d alpha. Okay, so we have to integrate. So once you will integrate this, you will find this expression that the magnetic field generated at this point, which is into this page, is defined as H is equals to I by 4 pi rho cos alpha 2 minus cos of alpha 1 into a phi. So this is the expression of magnetic field, or say magnetic field intensity, that is generated by this line segment. Okay, so if suppose you have to find the magnetic flux density, then what you have to do, you have to use this relationship so as to find out the magnetic flux density. Okay, so that's how we can use this Biot-Savart law for finding out, or say determine the value of magnetic field uh, from any structure, or say for any current carrying element. Similarly, in this problem we have to find out the magnetic field at point P, which is P here. Okay, here is the point P where we have to determine the magnetic field uh, from a single turn circular loop. So here a single turn circular loop uh, which is carrying current I, which is given here. Okay, so that how much magnetic field is generated by this current loop, that we have to determine at this point. So we have to use the same Biot-Savart law for determining that how much magnetic field that is generated by this singleton current carrying loop. Okay, dl cross uh, vector r over r cube. Okay, so here the differential length is taken as dl is equals to rho d phi a phi. Okay, along this, so this will be equals to rho d phi a phi. Okay, and vector r that we can calculate here as final minus initial, so this will be equals to 0 comma 0 comma h minus rho comma 0 comma 0. Okay, so this we defined as minus rho a rho plus h a z. Okay, so we can determine this dl cross vector r as this cross minus rho a rho plus h a z. Okay, so that we have to determine first. So this will be equals to a rho a phi and a z, and this is 0 rho d phi, and this will be 0, and here minus rho 0 and h. So we can determine this as rho h d phi a rho, then a phi term will be 0, and then a z plus a z rho square d phi. Okay, so this is the calculated value of dl cross r is vector r. Okay, so that we can put here So this B is defined as mu naught over 4 pi integral. Yeah, so this becomes equals to I, we can take outside here from this integral, and then this will be equals to rho h d phi a rho plus rho square d phi a z, okay, over r cube we can take as rho square plus h square raised to the power 3 by 2, okay, because r is given here, so we can obtain the modulus of r, that is magnitude, as rho square plus h square, so that we can put here instead of r, instead in the place of r cube, okay. So we have to determine this expression for determining the total magnetic field. So one thing that we have to see here, 1 minute. Yeah, so one thing that we have to see here, that due to this differential element we have obtained two different magnetic field components. One is along a row, that is along a row, and the another one is along a z, okay. So now we have, for solving this problem we have to consider the symmetry. So here you can see that here one more current element will be there in the 180-degree opposite to this current element that we are considering here, okay. So the current flowing through this is opposite to this current element, okay. So now for this current element the magnetic field is along, the arrow will be along this direction and az along this direction, okay. So what happen is that the radial component will cancel each other, okay. So the net field is along the az direction only, so we have to consider here radial component 0, okay. So B is defined as mu naught I by 4 pi integral rho square d phi az over rho square plus h square raised to the power 3 by 2, okay. And the value of phi d phi means integral limit we have to consider from 0 to 2 pi, okay. So now you can calculate the value of integral. So this becomes equals to mu naught by I, sorry, mu naught I by 4 pi. This will be equals to rho square by rho square plus h square raised to the power 3 by 2, and this integral becomes equals to 2 pi az, okay. So this will cancel each other. So the total magnetic field that, after calculation you will get this, okay. So that's how we can use the Biot-Savart law for determining the magnetic field, okay, from any current carrying element. So I hope this will be clear to you. So now moving to the next problem. So in this problem we have to determine the self inductance of the coaxial cable of inner radius A and outer radius B. So if suppose this is my coaxial cable where this is the inner conductor having a radius of A, whereas the outer conductor is defined by the radius of B, okay. So we have to determine the self inductance of this coaxial cable, okay. So for determining the total self inductance of this cable we have to uh, uh, basically determine two different inductance. One is the inductance that is existed inside this inner uh, conductor, and the another one is outside this conductor, okay, between these two conductors, okay. So the total inductance is defined as inductance that is inside this inner conductor and the inductance that is outside or say external this inner conductor, or say in between these two uh, conductors. Okay, because outside this total coaxial cable no field will be existed, because if suppose this is the amperian path, so the line integral of h dot dl is equals to total current that is enclosed in this amperian path. So this will cancel each other, that is plus I and minus I, so this will becomes equals to 0. So the total field outside this coaxial cable will be cancel each other, so no inductance will contribute out due to this outside field. Okay, so we have to determine this internal inductance and external inductance for determining the total inductance from this coaxial cable. Okay, so what I will do, yeah, so I will first determine the internal inductance, okay, and then I will determine the external inductance separately, and then I will add these two inductance for determining the total inductance. So here we have for determining the inductance, we know that this defined as flux linking through the coil divided by current flowing through the coil. Okay, so we have to first find out the flux. So flux we know that defined as b dot s, sorry, b dot s. Okay, so surface area we can calculate from this structure, but we have to determine that how much field that is linking through this structure. So for inner conductor, the total field that is calculated is given as b1 is equals to mu I rho over 2 pi a square a phi. Okay, whereas outside this inner conductor the field existing is defined as mu I over 2 pi rho. So these fields you can calculate by using ampere circuital law. Okay, so like here in the inner conductor, for determining that how much field is linking, so what you will do, you will take b dot dl is equals to mu into total current that is uh, existed inside this amperian path, which is defined as I into pi rho square over pi a square, because current that is inside this amperian path of radius rho is due to this factor only. Okay, so this is the total current that is passing through this amperian path. Okay, so this we defined as mu naught I rho square over a square, and this integral we can find as 2 pi into rho. So this rho will cancel, and that's how you can calculate the value of field, that is mu I rho over 2 pi a square. So that's how you can calculate the value of magnetic field inside this amperian path that is placed inside the inner conductor. Similarly for outer conductor, or say this amperian path, you can calculate as VO dot DL is equals to net current that is inside this conductor is I only. So this you can calculate as mu naught I by 2 pi rho. So that's how you can calculate the value of field that is flowing through the inner as well as uh, in between the conductors. Okay, so once you determine these fields, what we will do, we will use this field for determining the value of flux, which is defined here. Okay, so flux is also basically dependent on surface area, because as we know phi is defined as b dot s. Okay, so this is also dependent on the surface area, so that we can calculate as uh, yeah, B value we have already calculated, so I am considering it as B1. Okay, whereas for determining the DS, what we have to take, we have to first consider the total uh, area that is inside this Amperian loop, that is pi rho square over pi a square into d rho d yeah, dz. Okay, so this will cancel out, sorry, and the total flux, that is internal flux, is defined as b1 rho square by a square into d rho dz. Okay, so that's how you can calculate the internal flux. Okay, so now you have got this expression, you have to just put the value of b1 so as to obtain this expression. Okay, now you have to take limit, okay, integral limit for d rho and dz from 0 to a and 0 to l. Like here, the inner conductor is from 0 to a, which is the radius of this inner conductor, and length you can take anything, like here I am considering l. Okay, so once you will integrate this expression, you will find the flux that is passing through this inner conductor is defined as mu naught I l over 8 pi. Okay, so in inductance that is linked in the inner conductor is defined as flux over current passing through this inductor, which is equals to mu L over 8 pi. Similarly, or you can also determine the internal inductance per unit length, so you have to divide the inductance calculated with the length, overall length of the inductor. Okay, so that's how you can determine the uh, yeah, internal inductance. Okay, so now for determining the external inductance, what we have to do, we have already find out the value of b2, which is equals to mu I by 2 pi rho into a phi. Okay, and you have to just calculate the value of flux uh, that is contributed by this magnetic flux density, and take the ds as d rho dz. Okay, now you have to integrate this flux. Okay, so after that the expression that you will obtain is equal to mu l over 2 pi ln b by a. So you have to just sum up these two inductance, that is internal inductance and the external inductance, for determining the overall inductance of the coaxial cable. So that's how you can apply this Biot-Savart law and Ampere circuital law for determining inductance of any circuit or current carrying element. So I hope this will be clear to you. So thank you all.